Now, sample problem 3.10. This one is interesting because we've got this bracket here, and it has three cables attached at B, C, and D, right? And it states, replace the forces with an equivalent force couple system at A. How do we do it? What are we looking for? Maybe is a better question.
Single force.
We're looking for a single result force, right? Absolutely, at A, and its associated couple, right? For these three forces, they're going to generate R cross F, R cross F, and R cross F, right? So what we need to find are the position vectors from B with respect to A, C with respect to A, and then
T respect to
D with respect to A. Yeah? The interesting thing about this is the forces. Look at the forces. You've got this 1,000 Newton meter force, right? And that's located within the X, Z plane, right? So we can just simply reduce this, can't we, using basic right angle trig to find its X and K component, X and Z component, right? Here and here. Just remember that you got to add these algebraically. This is a negative, right? Negative Z, positive X. And then we've got a 1,200 Newton force acting within the IJ, right, or the XY. We've got a positive X and a positive Y. Cosine and sine respective, right? To find that one. How about the 700 Newton force? It's going from here to here. It's on a three-dimensional line, right?
Yeah.
How do we break that up into its component forces?
We're given you have the point at the end there, so you can use that and the position at B to determine its line of action. To get a direction vector.
Yes, I've been waiting for it. I knew it was coming. Yep, x2 minus x1, y2 minus y1, z2 minus z1, right? We can find the unit vector. And I can take that, take the square root of the sum of the squares of it to find its scalar magnitude, right? Divide that by each one of those respective x, y's, and z's. Multiply it by the scalar magnitude of the force, right? And we've got ourselves its rectangular components. Once I have the rectangular components of this force, that force, and this force, I can combine them, can't I? The IJKs. I can also find the cross products and of each one of these forces, B with respect to A, C with respect to A, and D with respect to A, and place them in three separate determinants. Resolve each one of those determinants, right? Because I have the position vectors. I have the R cross F, R cross F, R cross F. I resolve the three determinants into their component moments. And now I can combine the moments together, can't I? The I's, the J's, and the K's. So I have MX, MY, and MZ. Once I have MX, MY, and MZ, I can also combine these forces, FX, FY, and MZ. Now I have an FX, Y, and Z here, and an MX, Y, and Z here. If I want to reduce it further, all I got to do is take the square root of the sum of the squares, right? Pythagorean theorem for fx squared, fy squared, and fz squared, and square root of that is going to give me R. And then I got to find the direction cosines. That's correct, the angle, right? Fx over f, inverse cosine function, right? Fy over f, fz over, right? F. I find the direction, and I have to do the same exact thing with the moments. I add up the moments, ij's and k's. I get mxr, myr, and mzr, right? The resultant x, y, and z components of the moment. Take the square root of squares of those, and take mx over the resultant moment, cosine, my over its resultant, and mz over its resultant moment to get theta x, theta y, and theta z. So when I'm done, I'll have a force. I think it's going to look like this when I'm done. And it'll have a resulting moment based on those directions. And it's going to be perpendicular of the plane of the combination, right, of those three moments. So, that's a lot of work, isn't it? It took me like 2 minutes to describe it. But we have all the skills, right? We just broke these down into little separate pieces. And that's how you have, those are the critical thinking skills you need, right, to solve these problems. After that, it's just simple mathematics that everybody can do. Right? So, we talked it through. We already said the sum of the resultant, right? The resultant force is the sum of the forces, and the resultant moment is going to equal to the sum of the R cross S. Good. So let's take a look at it, right? And the first thing I did was set up the position vectors. RB with respect to A. With respect to A, that's RB with respect to A. It's gonna go from here to here, right? 0.075 positive I, right, meters. And there is no J to the point of application of that force. And then you have positive 0.05 K, right? Does everybody understand that? It's the position vector from here to here, right? Just going from here to here, positive, positive, good. The next one was RC with respect to A. With respect to A, I'm gonna go from here to here. We have, again, positive 0.075 I, right? And this time, negative 0.05 K, right? We're going into the plane. And there is no J for that one as well. D has an I and a J, but no K, right? D with respect to A, so with respect to A, I'm going from here to here. I'm gonna go here and here. So from there to there is, that's 100 millimeters, so it's positive 0.1 I, right? And from here to here, which is negative 0.1 J. Those are the three position vectors. That's the first row of my cross product, right? R cross F. Good. So now that I know the position vectors, I want to reduce each one of these forces into their componential form. Let's start with the tough one, right? FB. We know, like Patricia said, we have 2 points along that line. We can utilize the unit vector to break them up into the components, right? So, x2 minus x1, and that's 150, and x1 is 75. So 150 minus 75 is 75, it's millimeters, right? Yeah, millimeters. I, negative 50, J, plus 100, right?
Is it plus 75?
X2, Y2 minus Y1, right? Yeah, so it's negative 50 minus 100, right? So it's negative 150 millimeters J hat, right? And K hat is, that's 50, so we have 100 minus 50, right? So it's 50 plus 50 millimeters K hat. And this is equal to, I should call this is BE, right? Vector BE. And the scalar magnitude of that is just equal to the square root of some of the squares it is. 75 squared plus negative 150 squared plus 50 squared. And you're gonna get 175 millimeters, right? I noticed I skipped a step on the slide, so I'll just show it to you. That goes there. That goes there, right? And that's the unit vector along that line, BE, lambda BE. And we know that the rectangular component of the force for BE is going to be equal to the scalar magnitude of BE and its unit vector along that line. They gave us that. That's 700, right? So I just take 700 times that. 300, 700 times that is negative 600, 700 times that is 200. And this is the rectangular components, right? It's X, it's Y, and it's Z, right? With respect, right? That's its rectangular components of that force. Now that I have that, now I can just resolve these using simple right-angle trick, right? So FC is just 1,000 sine of cosine, 1,000 cosine of 45, 1,000 sine of 45. But the sine of 45 is going to be a negative value, right? Okay. So now we have the components of this force at C, and same thing here. We have cosine of 60, 1200 cosine 60 positive, and 1200 sine of 60, or cosine of 30, right? Also positive. So we should have an I and a J, both positives, which we do. The resultant force is 300, 700, 600, 1607, right? I. 1607 I plus J is negative 600, and 1,000, positive 1,039, so it's gonna be, let me write that here, 1607, newtons I plus 439 newtons J, and 200K minus 707 is minus 507 newtons K half. Does everybody understand? That's the resultant, right, in its vector form. So,
Oh, can you go back?
sure.
You're good.
You good? Okay. I'm only running, I don't know why I'm rushing, I still got like 7 minutes, we'll easily finish this problem in that time. I'm not gonna get the 4th today, but that's okay, we'll finish chapter 3 in its entirety. So, we resolved each one of these into their rectangular components, and I combined them, say that's my result in its component form. That is what's acting at X, right? Plus, there are 3 couples. Right? Those are the components for, right, the 3 different forces. And to now determine what the resultant couple is going to be, I got to do R cross F, R cross F, R cross F. I have the position vectors, and I've got the force vectors, right? Write it in its component form. I just stacked them in this case, right? It's a sum of them. B with respect to A, 0.075, 0.05, 0.075, 0.05, right? And so on. I should have brought these over. So on and so forth, right? R cross F. Oops, this is, yeah, 300, negative 600, 200. Yeah, that's IJK for the first force, right? And the second one was 700 and negative 700. And then the last one was 600 and 1,039, I and J. That came from, right? There, there, and there. Once I have these in their 3 separate determinants, I resolve these determinants, right? We all know how to do that. We got 30I minus 45K, 17.68J, does that make sense? C with respect to A, it's just gonna have a J. C with respect to A, that force and that force is just gonna do that, no doubt, right? That force is gonna have a rotation like this, and this force is gonna have a rotation like this, but the combination thereof, right? It's got to be, it's just a J, and that one beats 17.68J. And that's because this is bigger than that, right? That's the only reason why. And then a D, right? R cross F to here, got 163.9. So the resultant couple is just adding up the components, right? This has an MX, MZ, MY, and an MZ. MX, only MX, the only MY, and the MZ is 163 minus 45 is 118. Does that make sense? And then I could show that like this, in its component form, right? We had 1607, and then we had its generating couple of 30, right? And then you have 439 force, and its generating couple of 17.68, and then you had a 1607 force, and its generating couple of 118.9 in the K. So we have a force that's acting like this, right, when it's all said and done, which I can find by just taking the square root of some of the squares, right, of this, and finding its direction cosines, and we'll have a couple that also can be done, square root of some of the squares, and that is gonna generate a couple that's gonna be close to, right? It's not gonna be on this, oh, actually, it will be on the same line, won't it? It'll be on the same. I'm not sure about that, we'd have to look into that a little further. But we will have a couple generating a similar rotation along it, right? Coming out of the board in this direction like that, for sure. Yes?
So now that you've gotten to this stage, where you have the resultant of the forces themselves, and then the sum of the moments.
Mm-hmm.
If you really wanted to, you could do what we did for the previous problems, right, and reduce that further to just one singular.
In this case, I can't, because they're not mutually perpendicular.
Oh, that's right, that's right,
Yeah,
that's right.
That's the only problem with
That's
that,
right.
yeah. All right, what do you guys think?